Now in this lecture we find out the length of line segment AP is equals to x. In the drawing we have a circle that is inscribed by this right triangle, triangle ABC. You know that side AC, the opposite is tangent to the circle at point P. We also have here line segment SP that cuts the circle at points Q and P. Again, our task is to find out the length of line segment AP is equals to x. We have to find out the value of x. In addition, we know that line segment SQ, QS equals to 25 units in its length. This is line segment QP or chord QP is equals to 24 units in its length. Okay, again, our task is to find out the length of line segment AP, this line segment AP is equals to x. We have to find out the value of x. So first of all, we know that SC, line segment SC is a straight line, and according to rule 3, the sum of the areas on one side of a straight line is equal to 180 degrees. So the sum of the areas on the upper side of the straight line AC at point B must be equal to 180 degrees according to rule 3. So which areas we have at the upper side of AC at point B? We have this area that is right angle plus this missing angle, so that the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. According to rule 3, of course. So here we can implement, first of all we define the point of tendency of tangent SC with this circle. This point is point M. So here we can implement rule 2 in our drawing. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from convex point to a circle are equal. So in the drawing we have a circle. This is the convex point, point P. From this convex point P, we have two tangents to the circle. Tangent PA and tangent PB. And according to this rule, all two they are equal to each other in their lengths. That is to say, PA equals to PB. So we can actually implement rule 2 in our drawing. One, if you focus this convex point A, from this convex point A, we have two tangents to this circle, tangent AQ and tangent AP. According to all two, they are equal to each other. That is to say, AP, tangent AP equals to tangent AQ. AP equals to AQ, according to rule 2. AP equals to AQ. But it is given as a question that AQ equals to x. So you can write here that AP equals to x. And for this equation x equals to AP equals to AQ, we know that AQ also equals to x units in its length. Likewise, and focus on this convex point B. From this convex point B, we have two tangents to this circle. Tangent BM and tangent BQ, and according to rule 2 they are equal to each other. That is to say, BM equals to BQ. BM equals to BQ. So if we define the length of tangent BM as A, then the length of tangent BQ must be also equal to A because they are equal to each other according to rule 2. Okay. So, in the next step, we will do a construction, that is to say, from point A. So actually, you can see that triangle AQP is an associated triangle. Again, triangle AQP is an associated triangle. Why? Because side AQ of triangle AQP equals to side AP. Therefore, this is an associated triangle. And PQ is of course the best of this associated triangle, triangle APQ. So from point A, we will go perpendicular to the base QP of the associated triangle, triangle AQP. So here, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So define the touching point of the perpendicular from point A and the base QP. This point is point Z. So here we can implement Rule 21. Perpendicular on Rule 21. According to Rule 21, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have the associated triangle ABC. Side AB equals to side AC, and the triangle ABC is an associated triangle. So, from point A, we draw perpendicular AO to the base BC. Again, from point A, we draw perpendicular AO to the base BC. And according to this Rule 21, the perpendicular AO bisects base BC. Again, the perpendicular AO bisects the base BC. This is to say, it divides the base BC into two halves. The first half is BO, the second half is CO, and of course the first half BO equals to CO. So BO equals to CO, and each half equals to BC over 2. Again, BO equals to CO equals to BC over 2. So we can implement Rule 21 in our drawing. In our drawing, from point A, we draw perpendicular to the base QP. This is a associated triangle, triangle AQP. Again, from point A, we draw perpendicular to the base QP of this associated triangle, triangle APQ. So AZ is the perpendicular to the base QP of the associated triangle, triangle AQP. And according to Rule 21, the perpendicular AZ bisects the perpendicular AZ bisects the base QP. This is to say, it divides the base QP into two halves. The first half is QZ. It equals to 4 to the second half ZP. So according to Rule 2, the associated triangle, triangle AQP, QZ equals to ZP, and each half equals to QP over 2. Each half equals to QP over 2. QP is 24, therefore QP over 2 is 24 over 2, that is 12. So we found out that each half equals to 12 units in its length. The first half QE equals to 12, the second half EP also equals to 12 units in its length. Okay, so in the first step, we will implement Rule 10 in our drawing. And please click on Rule 10. Rule 10 is true in any circle, so in any circle, if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So in the drawing, we have a circle. This is tangent PT, that is tangent to the circle point T. In addition, we have chord BA, this is chord BA of the circle. Then we extended chord BA in such a way that it will touch this common exam point P. Again, we extended chord BA in such a way that it touches the common exam point P. So in this drawing, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can implement Rule 10, this Rule 10 in our drawing. Right, in our drawing, if we focus on this common exam point S, from this common exam point S, we have tangent SM of this circle that is tangent to this circle at point N. In addition, we have here chord PQ that is extended in such a way that it touches the connection point S. So all the requirements for rule 10 are satisfied, and therefore we can implement a rule 10. According to rule 10, we get that the following equation is true. So the connection point P. The following equation is true. That Sm square, that is the square of the tangent, equals to Sq times Sp. And again, if you focus on the connection point S, the following equation is true. This Sm squared, that is the square of the tangent, equals to Sq times Sp. Again, Sm square equals to Sq times Sm. Sm square equals to Sq times Sp. Again, Sm square equals to Sq times Sp. This equation is the implementation of rule 10 in our drawing. So Sm square equals to SQ. SQ is 25, so let's substitute SQ by 25 times SP. SP in total equals to SQ plus QP. So in total, SP equals to SQ, that is 25, plus QP, that is 24. So in total, SP equals to 49. So if you found out that SM square equals to 25 times 49. Here we take out of this equation, and finally get that the length of tangent SM is equal to the square root of 25 times 49. So SM equals to the square root of 25 is 5 times the square root of 49 is 7. So in total, Sm equals to 5 times 7, that is 35. Sm equals to 35 units in its length. So this is tangent Sm, that equals to 25 units in its length. 29. Sm equals to 35 units in its length. What is the length of this line segment SB or side SB? From the drawing, it is very easy to see that SB in total equals to SM minus BM. Again, SB equals to SM minus BM. So, write down SB equals to SM minus BM. So in total, SB equals to SM, that is 35, minus BM. BM equals to A according to our definition. So in total, SB equals to 35 minus units in its length. This is side SB, that equals to 35 minus units in its length. So in the next step, we'll focus on this right triangle SQB, and we'll implement the Pythagoras theorem on this right triangle SQB. So according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle SQB, here by PT is the evaluation for Pythagoras theorem. So in the right triangle SQB, SQ squared, that is the square of the hypotenuse, equals to QB squared, plus bs squared. So I write it down. SQ squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. And again, according to the Pythagoras theorem, this item SQB, the following equation is true. That SQ squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. SQ is 25, therefore SQ squared is 25 squared, that is 625. And it is equal to QB squared. QB is A, therefore QB squared is A squared plus SB squared. SB is 35 minus A, therefore SB squared is 35 minus A squared. So in total, we should find out that 625 equals to A squared plus 35 minus A squared. Here we'll open the brackets of this expression and we get that 625 625 equals to A squared plus 35 minus A squared. 35 minus A squared equals to 35 squared. That is 1225 plus A squared minus 2 times 35 times 8, that is minus 78. Here we subtract 625 from this equation. 0 equals to A squared plus A squared is 2A squared minus 78. 1225 minus 625 is 600. So in total we found out that 0 equals to 2A squared minus 78 plus 600. Here we divide this equation by 2. And finally you get that 2A squared over 2 is A squared. Minus 78 over 2 is minus 35A. And 600 over 2 is 300 equals to 0. So A squared minus 35A minus 35A plus 300 equals to 0. So this is the quadratic equation. A squared plus 35A plus 300 equals to 0. And again, this is a quadratic equation. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. This general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. When you find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. A, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. So in our specific case, a squared minus 45a plus 300 equals to 0. The coefficient a equals to 1. The coefficient b equals to minus 35. And the coefficient c equals to 300. And the variable that we are looking for in this question is the variable a. So x equals to a. So we put the data inside this general formula for x, and this way we find out the value of the values of a, because the variable that we are looking for in this question is a. So x equals to a, so we substitute x by a, and we get that a equals to minus b. B equals to minus 35, therefore minus b is minus 35, that is 35, plus minus square root of b squared. B is minus 35, therefore minus b squared, therefore b squared is minus 45 squared, that is 1225, minus 4 times a times c. A is 1, so minus 4 times 1 is minus 4 times c. Minus 4 times c is minus 4 times 300, that is minus 1200. Divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in total, we found out that a equals to 35 plus minus the square root of 1225 minus 1200 is 25. So inside the root we left only with 25 over 2. So a equals to 35 plus minus, and the square root of 25 is 5. So in total, I should find out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is a equals to 20, while the second solution for a is a equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. The second solution for a is a equals to 15. The first solution for a is a equals to 20. Okay, we have two solutions for a. We know that vertex angles are equal to each other. Those two angles are defined as vertex angles, and they are equal to each other in their sizes. So if the size of this vertex angle is alpha, then the size of this vertex angle are also equal to alpha, according to the rule I mentioned. So in this right triangle AZQ, this angle equals to 90 degrees, this angle equals to alpha, and therefore this first piece angle must be equal to 90 degrees minus alpha. Why? Because in this right triangle AZQ, 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this triangle the right triangle SQB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third angle must be equal to 90 degrees minus alpha for the same reason. That this angle equals to 90 degrees minus alpha. Okay. This angle must be equal to 90 degrees minus alpha, according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very easy to see that those two triangles are similar to each other according to angle similarity rule. Okay, again, it is very easy to see that the right triangle AQZ is similar to this right triangle QBS according to angle similarity rule. Why? The fact that those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So I shall find out that all the triangles in this green right triangle SQB are corresponding equal to all those triangles in this right triangle AZQ. Therefore, those two right triangles are similar to each other according to angle, similarity rule. So I write it down. I shall find out that the green triangle SQB, the green right triangle SQB, is similar, this is the sign of similar, to this right triangle AQZ according to angle, similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side SQ of this green right triangle SQB over side AQ of this right triangle AQZ is equal to side QB of this green right triangle SQB over side QZ of this right triangle AZQ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of the right triangle SQB of side AQ of the right triangle AQZ is equals to side QB of the right triangle SQB or side ZQ of the right triangle AZQ. SQ is 25 over AQ. AQ is X, and it is equal to QB. QB is A, according to our definition, or QZ. We already found out that QZ equals to 12 units in its length. So in total, we actually found out that 25 over X equals to A over 12. Here we of course multiply this equation, and finally we get that 25 times 12 equals to 8 times X. 25 times 12 is 300, so 300 equals to 8 times X. So in the next step, I'll copy this right triangle ABC in the new page, and we analyze this triangle. Okay, this is right triangle ABC that I copied from this original drawing. This is the point. This is the point of tendency of triangle BC. This is equal to M according to our definition. Here we have already found out that VM equals to A and QB also equals to A. AQ equals to X. In the next step, we define the center of this circle. This point is point O. Point M is the point of tendency of tangent BC with this circle. We join points O and M together by straight line. define the radius of this circle as R. Point O is the center of this circle, point M is the point of the circle itself, therefore OM is the radius of this circle. This is equal to R according to our definition. The radius OM is equal to R, the radius OM is drawn to point M, that is the point of tendency BC with this circle. And now your radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MQ. If BC is perpendicular to MQ, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Point Q is the point of tendency of tangent AB with this circle. So in the next step, we join points O and Q together by a side line. OQ is, of course, the radius of this circle, that equals to R. Not a bit on the same explanation. Point Q is the point of tendency of tangent AB with this circle. So, according to 1, this angle equals to 90 degrees. And this angle also equals to 90 degrees. So, in quadrilateral OQBM, we have 1, 2, 3 angles, and therefore this fourth missing angle must be also equal to 90 degrees in its size, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral QOMB, we have 4 right angles, and therefore it is a rectangle. So we know that the opposite sides of a rectangle are equal to each other. This is a rectangle. Again, we know that the opposite sides of a rectangle are equal to each other. So, in rectangle QOMB, side OM equals to the opposite side QB, but OM is R, therefore the opposite side QB must be also equal to R units in its length. It is actually equal to the radius of the circle, that is R. So QB equals to A and A equals to R. Okay. In the next step, we'll extend the radius MO is equals to R. We'll extend the radius MO until it touches the circle. When you find the touching point of the extended radius MO with this circle, this point is point Z. The radius OM is absolutely a side line. When you extend the side line by side line, the result MZ must be also a side line. So MZ is a side line, MZ is a chord that passes through the center of the circle, and therefore MZ is the diameter of the circle. So point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle that is equals to R. Again, MZ is the diameter of the circle, and therefore it is absolutely a side line. So if you focus on the left side of the side line MZ at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of the side line is equal to 180 degrees. So which angles we have the left side of the diameter ZM at point O, we have this angle that is the right angle, plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, from AB we will go perpendicular. From AB we will go tangent to the circle at point Z. Again, from AB we will go tangent to the circle that will be tangent to the circle at point Z. You define the touching point of the tangent with side AB. This point is point T. Again, TZ is a tangent to the circle at point Z. So the radius OZ is equals to R. The radius OZ is drawn to point Z. It is the point of tendency of tangent TZ with this circle. And now you reduce Z 1 to the power of 10 Z, then tangent Tz will be perpendicular to the radius ZO. If Tz is perpendicular to ZO, it means that this angle equals to 90 degrees according to rule 1. So in quadrangle Tz or Q, we have 1, 2, 3 letters, and therefore this fourth is must be equal to 90 degrees in size. So in quadrangle TQ ZO, we have 4 rectangles, and therefore it is a rectangle. And you know that the opposite sides of rectangle are equal to each other. So in rectangle TZ or Q, side ZO must be equal to the opposite side TQ. But ZO is out, therefore the opposite side TQ must be also equal to R units in its length. Okay, so QB equals to R and R, QB equals to A equals to R. So QB equals to A and A equals to R. QB is definitely less than AQ. AQ equals to AT plus TQ. AQ equals to AT plus TQ. So it is AT plus CQ, that is R. So it is AT plus R. And it is equals to AT plus R equals to AQ. Okay? AT plus R equals to AQ. And AQ equals to X. We already found out that AQ equals to X. So from this long inequality, QB equals to A equals to R, it is less than AT plus R equals to AQ equals to X. We derive that A is less than R. So we can write here that QB equals to A. And from this long equation, inequality, we derive that A is less than X. A is less than X. Actually, it is very clear that A is less than X because A equals to R and X equals to AT plus R. It is very clear that AT plus R must be greater than R because AT is a positive number. So it is very clear that AT plus R must be greater than R. In total, I should find out that X is greater than A. X is greater than A. And by solving this quadratic equation, we arrive to two results. The first result is A equals to 20, and the second result is A equals to 15. Repeat again. By solving the quadratic equation, we arrive to two results. The first result is A equals to 15, the second result is A equals to 20. So we have two solutions that are possible for A. And again, we have two solutions that are possible for A. The first solution for A is that A equals to 20, while the second solution is A equals to 15. We already found out that $300 equals to A times X. So here we divide this equation by A. We get that X This is allowable to divide the equation by a because a is a positive number, it is a length. So we divide this equation by a and we get that x equals to 300 over a. So x equals to 300 over a. So if a equals to 15, then 300 over a is 300 over 15. This is 20. So when a equals to 15, x equals to 20. But if a equals to 20, then x equals to 300 over a. So a is 20, so it is 300 over 20, that is 15. So if a equals to 20, then x equals to 15. Repeat again, we actually found out that we only found out that x must be greater than a. Repeat again. We only found out that x must be greater than a. We found out that x must be greater than a. We can argue that x must be greater than a. So if a equals to 20, x equals to 15. Definitely x is less than a. Again, if x equals to 15, then a equals to 20. So x is equals to 15 is less than 20. 15 is less than 20. From this inequality, we learn that a is less than a, and that x is less than a. X is less than a. But x must be greater than a, so it is a contradiction. So the result that x must be greater than a, so this solution is incorrect solution, we get the solution. But here we have, if x equals to 20, then a equals to 15, so 20 is definitely greater than 15. So if x equals to 20, then a equals to 15, and x is definitely greater than 20 is greater than 15, so x is equals to 20 is greater than 8 is equals to 15. On this inequality, we derive that x is indeed greater than a, exactly like the result that we got it, that x must be greater than a. Therefore, the only solution that is possible for a is a equals to 15, and then x equals to 20. So the answer to the question is that AP is equals to x is equal to 20 units in its term. That is the answer to the question. If again, I found out that line segment AP is equals to x is equal to 20 units in its length. Okay, so the next step, I'll start the lecture. our task in this question is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So in the drawing, we have a circle that is described by the right triangle ABC. This is line segment SP that cuts this circle 2 points Q and P. And SC is a side line. That is, it is actually tangent SC. That is tangent to this circle. It's point M. We also know that line segment QS equals to 25 units in its length. Line segment QP equals to 24 units in its length. Again, our task is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So first of all, according to all three, the sum of the angles on one side of a straight line is equal to 180 degrees. SC is a tangent. SC is a tangent. It is absolutely a straight line. So if we focus on the upper side of the straight line AC at point B, the sum of the angles must be equal to 180 degrees according to all three. All three state that the sum of the angles on one side of a straight line is equal to 180 degrees. So in each case we have the upper side of SC at point B, we have this angle that is the right angle, plus this missing angle, total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we implement rule 2 in our drawing. Let's make it on rule 2. According to rule 2, the lengths of two tangents from a common center point to a circle are equal. So in the drawing, we have a circle. This is the common center point, point P. From this common center point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, the lengths of those two tangents must be equal to each other. That is to say, PA equals to PB. So if we actually implement rule 2 in our drawing. Now it is in our drawing. If we focus on this common center point A, from this common center point A, we have two tangents to this circle, tangent AQ and tangent AP. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP is x, therefore AQ must be also equal to x units in its length. Likewise, if we focus on this common center, we define the touching point of the tangent SC with this circle. This point is point N. So if we focus on this common center point B, from this common center point B, we have two tangents to this circle, tangent BM and tangent PQ. Q is tangent, actually tangent AB is tangent to the circle at point Q. Therefore BQ is a tangent. So on the common center point B, we have two tangents to this circle, tangent BQ and tangent BM. According to all two, they are equal to each other. That is to say, BQ equals to BM. So if we define BM as A, then BQ must be also equal to A because they are equal to each other according to all two. So in the next step, we implemented all 10 in our all 21 in our drawing. Triangle AQP is an associated triangle because AP equals to AQ. QP is of course the base of the associated triangle AQP. From the vertex A of this associated triangle, we go perpendicular to the base QP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and QP. This point is point Z. So here we can implement all 21 according to all 21. The perpendicular to the base of an associated triangle bisect the base. In the drawing, the associated triangle ABC. AB equals to AC. BC is of course the base of this associated triangle. BC is the base of this associated triangle ABC. From point A, we do perpendicular to the base BC. Again, from point A, we do perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So the touching point of the perpendicular from point A and BC, this point is defined as AO. So according to this rule, all 21, the perpendicular AO bisect BC. Again, the perpendicular AO bisect base BC. That is to say, it divides the base BC into two halves. The first half is BC, this is the first half, that is VO. This is the second half, that is OC. And each half, of course, equals to BC over 2. It has been bisected by the perpendicular AO. So the first half, VO equals to BC over 2. The second half also equals to BC over 2. So you can actually implement all 21 in this associated triangle APQ. According to all 21, the perpendicular AZ bisects the base QP. So the first half equals to QP over 2. This is the second half of the base QP. This is equal, QZ equals to QP over 2. Again, QP equals to QZ. QP equals to QZ. And each half equals to QP over 2. QP equals to QZ equals to QP over 2. But QP is 24. Therefore, QP over 2 is 24 over 2, that is 12. So the first half QZ is 12, the second half ZP is also 12 units in its length. So in the next step, we implemented all 10 in our drawing. If you focus on this connection point C, from this, if you focus on this connection point S, from this connection point F, we have tangent SM. To this circle that is centered to this circle at point M. Likewise, we have here chord QP that is extended until it touches the connection point S. So all the requirements for full 10 are satisfied, and therefore we can implement here all 10. Okay, click here on all 10. In any circle, if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So in the following, we have a circle. This is tangent AT, this is tangent PT, that is tangent to this circle at point T. Likewise, we have here chord AB that is extended until it touches this connection point P. So in this moment, the following equation is true, that PT square equals to PA times PB. Again, PT square equals to PA times PB. So we can implement all 10 in our drawing. So if you focus on this connection point S, according to all 10, PM square, SM square, this is the square of the tangent, must be equal to SQ times SP. Again, SM square equals to SQ times SP. So to all 10, if you focus on the connection point S, the following equation is true, that SM square equals to SQ times SP. SM is the missing side, so it is it is. SQ is 25, and QP is 24. Again, SQ is 25, and SP in total equals to SQ, that is 25, plus QP, that is 24. So in total, SP equals to 25 plus 24, that is 49. So SM square equals to SQ, that is 25, times SP, that is 49. Here we took a root out of this equation and finally found out that there is an opposite to SM equals to the square root of 25 times 49. The square root of 25 is 5 and the square root of 49 is 7. So in total, SM equals to 5 times 7, that is 45. The length of the opposite SM is equal to 45 units in its length. So what is the length of SB? SB equals to SM once BM. Again, SB in total equals to SM once BM. And again, yeah, SB equals to SM once BM. So SB in total equals to SM, that is 35, once BM, that is 8. So in total, SB equals to 35 once units in its length. So in the next step, we implement the Pythagoras theorem on this right green triangle SQB. According to the Pythagoras theorem, in this right triangle SQB, SQ squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. Again, SQ squared, that is the square of the hypotenuse, equals to QB squared plus BS squared. The argument are SQB, SQ squared, that is the square of the hypotenuse, equals to QB squared plus SB squared. SQ is 25, therefore SQ squared is 25 squared, that is 625, and it equals to QB squared. QB is 8, therefore QB squared is 8 squared, plus SB squared. SB is 35 minus 8, therefore SB is 35 minus 8 squared. So total 625 equals to 8 squared plus 35 minus 8 squared. 35 minus 8 squared equals to 35 squared, that is 1225, plus 8 squared, plus 2 times 35 times 8, that is minus 78. So here we subtract 625 from this equation, so in this side of the equation we left with nothing, that is to say 0, while on the other side of the equation we have a squared plus a squared, that is 2a squared, minus 78, and 1225 minus 625 is 600. So in total we found out that 0 equals to 2a squared minus 78 plus 600. Here we divided this equation by 2 and finally found out that 2a squared over 2 is a squared, minus 78 over 2 is minus 45a, and 600 over 2 is 300. So in total we found out that a squared minus 35a plus 300 equals to 0. And again we found out that a squared plus 45a plus 300 equals to 0. So here this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here, this equation a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to minus 35, and the coefficient c equals to 300. And the variable that we are looking for in this quadratic equation, now quadratic equation is a, so x equals to a. So the only thing that is left to do is to put the data of this quadratic, specific quadratic equation, this general formula for x, and this way we find out the value of the values of a, because x equals to a. So we did it, and actually found out again x equals to a, so a equals to minus b, b is minus 45, therefore minus b is minus 45, that is 35 plus minus square root of b squared. b is minus 45, therefore b squared is minus 45 squared, that is 1225 minus 4 times a times c. So a is minus 4 times 1 is minus 4 times c. Minus 4 times c, that is 300, minus 4 times 300 is minus 1200. So inside the root we have 1225 minus 1200 over 2a. A is 1, so 2a is 2 times 1, that is 2. So a equals to 35 plus minus 1225 minus 1200 is 25. So inside the root we have 25 over 2. So in total we found out that a equals to 35 plus minus, the square root of 25 is 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 35 plus 5 is 40, 40 over 2 is 20. So the first solution for a is that a equals to 20, while the other solution for a is that a equals to 35 minus a over 2, 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for a is 15, the first solution for a is 20. So in the next step, we found out that those two right triangles are similar to each other. Why those two right triangles are similar to each other? First of all, those angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if we define the size of this vertex angles as a, then the size of this vertex angles must be also equal to a, because they are equal to each other. So in this triangle A, Z, the right triangle is in Q. This angle equals to alpha, this angle equals to 90 degrees, and therefore this this angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, in this great triangle, the great right triangle QBS, this angle equals to alpha, this angle equals to 90 degrees, and therefore this angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It is very clear that those two right triangles are similar to each other. Why? Because of the fact that those two angles are both equal to alpha and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha and therefore they are equal to each other. So if you find out that all those three angles, this triangle, right triangle QBS are corresponding equal to all those three angles in this right triangle AQZ. And therefore those two right triangles are similar to each other according to again similarity rule. Okay, again, if you found out that the right triangle SQB are similar to the right triangle AQZ according to again similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that the side SQ of this right triangle SQB or the side AQ of this right triangle AQZ is equals to side QB of this right triangle SQB, or side QZ of this right triangle AQZ. Okay, again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive the side SQ of the right triangle SQB or side AO of the right triangle AQZ is equals to side QB of the right triangle SQB or side QZ of the right triangle AQZ. SQ is 25, AQ is X, QB is A, and QZ is 12. So in total, we should find out that 25 over X equals to A over 12. Here we cross multiply this equation and find out that 25 times 12 equals to A times X. 25 times 12 is 300. So in total, AX equals to 300. We divided the equation by A and found out that X equals to 300 over A. So in the next step, I copied. So actually, we have two solutions for A. A either equals to 20 or 15. But we have to verify that which solution is the right solution. In order to find out which solution is the right solution for us, I copied this right triangle with the circle in a new drawing, and you analyze this triangle with the circle. This is the right triangle ABC that I copied from the original drawing. So we define the center of this circle. This point is point O. Point Q is the point of tendency of tangent AB with this circle. We join points O and Q together by straight line. Point O is the center of the circle. Point Q is the center is the point of the circle Z. Therefore, AQ is the radius of the circle that is equals to R according to our definition. Likewise, point M is the point of tendency of tangent BC with this circle. We join points O and M together by straight line. OM is of course the radius of the circle is equal to R. Again, according to rule 1, this angle equals to 90 degrees and this angle equals to 90 degrees. Repeat again on rule 1. The radius of M is equals to R. The radius of M is 1 to point M, that is the point of tendency of tangent BC with this circle. And now, if our radius is 1 to the point of tendency, then tangent BC will be perpendicular to the radius of MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Likewise, I'll not repeat on the same explanation. Point Q is the point of tendency of tangent AB with this circle. Therefore, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in this small polynomial QOMB, we have 1, 2, 3 angles, and therefore this fourth mixed angle must be equal to 90 degrees in size according to the rule that the sum of the angles in any one angle is equal to 160 degrees. In the next step, we extended radius MO by straight line until it touches the circle at point Z. We extend the straight line by straight line. The result MZ is also a straight line, must be a straight line. MZ is a chord that passes through the center of the circle and therefore it is the diameter. point O is the center of the circle, point Z is the point of the circle Z, therefore OZ is the radius of the circle is equals to R. So MZ is a diameter, it is absolutely a straight line. So if you focus on the right side of the straight line MZ at point O, the sum of the angles must be equal to 180 degrees according to rule of 3. So which angles we have at the right side of MO at point of the right side of the straight line MZ at point O, we have this angle that is the right angle plus this missing angle, and total the sum of those two angles must be equal to 180 degrees according to rule of 3. Therefore, this missing angle must be equal to 90 degrees in its size. The next step, from AB, we do tangent to the circle at point Z. We do a tangent that will be tangent to the circle at point Z. Okay, we find this point, that is the touching point of the tangent with side AB. This point is point T. So TZ is a tangent to the circle at point Z. OZ is the radius R, that is 1 to point Z, that is the point of tendency of tangent TZ with this circle. And whenever your radius that is 1 to the point of tendency, then tangent TZ will be perpendicular to the radius OZ. If TZ is perpendicular to OZ, it means that this angle equals to 90 degrees according to rule 1. So in total, in the small quadrilateral TZ or Q, we have 1, 2 right angles. This angle equals to 90 degrees according to rule 3. So we have 1, 2 right angles, and therefore this 4 minutes angle must be equal to 90 degrees in its size. Therefore, this quadrilateral is a rectangle. We know that the opposite sides of a rectangle are equal to each other. So in rectangle TZOM or Q, side ZO must be equal to the opposite side TQ, but ZO is out, therefore the opposite side TQ must be also equal to 1 minus in its length. So here we have QB equals to A and is equals to R. AQ equals to AT plus TQ. So it is AT plus TQ. TQ is also in total AQ equals to AT plus R. And this equals to X according to what is given in the question. So we have here so as I mentioned before, QB equals to A and A equals to R. Again, QB equals to A and A equals to R. And it is definitely less than AQ. AQ equals to AT plus TQ, is actually AT plus R. AT plus R, and AT plus R equals to AQ. And AT plus R equals to AQ, and according to what we already found out, AT equals to AQ equals to X. So from this log equation, from this log inequality, we derive that A is smaller than X. And A is smaller than X. It is very clear that A is smaller than X because A equals to R, while X equals to AT plus R. AT is a positive number, therefore X is equal to AT plus R must be greater than R, this way. So in total we found out that A is less than X. A is less than X. A is equal to QB is less than AQ is equal to X. A is less than X, or X is greater than A. But again, we found out that X is greater than A. We have two solutions for A according to the solution of the quadratic equation. The first solution for A is that A equals to 20, while the second solution for A is that A equals to 15. And we have the equation, we only found out that A times X equals to 300. And again, we already found out that a times x equals to 300. And again, we already found out that a times x equals to 300. Here we divided this equation by n, and we found out that x equals to 300 over a. Yeah, x equals to 300 over a. So if a equals to 15, it means that 300 over a is 300 over 15, that is 20. So if a equals to 15, then x equals to 20. So x equals to 20, it is definitely greater than a equals to 15, because 20 is greater than 15. So according to the solution that a equals to 15, we get that x is indeed greater than a, because 20 is greater than 15. So found out that x is greater than a according to these findings. X equals to x is greater than a. But according to the second solution for a, if a equals to 20, then 300 over a is 300 over 20, that is 15. So then x equals to 15. So if x equals to 15, it is less than a is equals to 20, because 15 is less than 20. So from this inequality, we get that x is less than a, but x must be greater than a. So it is a contradiction to the findings. Due to the contradiction, we arrive to the conclusion that this solution is the incorrect solution, and the only solution that is possible for a, that is a equals to 15, and therefore x must be equal to 20 units in its length. So the solution to the question is that answer that AP is equals to x is equal to 20 units in its length. Okay, thank you very much.